Okay, so I will apologize for speaking in English. I offered the choice of Latin or French or Russian or Korean or Chinese, but Dutch is not one of my choices, so English seemed like the best one. Okay, so gravitational waves. They're a prediction of Einstein's theory of general relativity. And just to remind you, before there was general relativity, there was special relativity from 1905. And Einstein's insight of special relativity was that in our ordinary daily life, space and time are very different things. I can move in space any direction I want, but time seems to force me to go in one direction, and there's a very clear difference between space and time. But Einstein realized that that's just because we're moving slowly, and if you start moving rapidly, then space and time get mixed up, and different observers disagree on what is space and time. And one of the consequences of that was the equivalence of mass and energy, so mass can be converted into energy and vice versa. And we've tested all of these remarkable discoveries to very high precision, in particle accelerators in particular, so we know special relativity is extremely precise and very accurate. Now, 10 years later, after 10 years of hard work, Einstein developed his general theory of relativity. And the general theory of relativity makes space and time, rather than just a single four-dimensional but still sort of Cartesian coordinate system, it proposes that space and time are actually curved, and that gravity is not actually a force in the sense that electromagnetic or strong forces are forces. It's just a consequence of the curvature of space-time, and that's the reason why everything falls at the same rate, and why you can get rid of gravity by freely falling in the space station, for example. So particles in this curved space-time follow what their definition of a straight line. A straight line is the shortest distance between 2 points, and it looks straight if the space-time is flat, but if it's curved, the shortest distance between 2 points becomes a curve, and those are the orbits of freely falling bodies. So until this year, general relativity had really only been tested for slow speeds like those in the solar system or orbiting neutron stars and pulsars, and rather weak gravitational potentials. So the real excitement is that we now have evidence that general relativity really works for velocities of order the speed of light in very deep gravitational potentials. So here's the traditional picture of a slice of space, no time shown and no third dimension of space because they don't fit on the flat screen very well. But this gives you the idea that if I have some heavy masses, they curve the space-time, and so if I calculate the shortest distance between this point and this point, it's no longer a straight line, but it sort of dips down and comes out again. Now, one of the really remarkable things about the theory of general relativity is that space-time curvature in the theory actually has energy, and therefore mass. So a curved space-time can curve itself. If I have curvature in the space-time, that acts like mass and energy in that curved space. So even in the absence of any mass or energy, I can set up a system which is an extremely curved space-time. And this example shown here is a black hole, actually two black holes. And the fact that it's vertical here rather than having the nice smooth little curve on the bottom is a consequence of the fact that you would have to move at the speed of light to try to escape from this. So the black holes are examples of things with space-time curvature in space and time maintaining itself without any matter, and gravitational waves are another example. So to try to explain to you where gravitational waves come from, let me remind you about lines of force. So if I have an electric charge and I put another charge somewhere, these lines of force are defined to define the direction that the force between this charge and another charge would have. And the strength goes like 1 over the area between the lines of force. Now, in gravity, I could do exactly the same thing. Gravitational forces are gm over r squared, just like charge over r squared. So the Newtonian lines of gravitational force would look exactly the same. So the one difference is that gravitational lines of force don't have the same meaning as they do for charges, because I can measure the electric force between two charges just by putting two charges next to each other. One defines the force fields, and the other one I use to measure the force field. In gravity, I can't do that because you know that if I freely fall, all the gravity disappears. So if I have one particle that's freely falling, there's no way I can define the gravitational field in an observer-independent way. But if I have two particles that are nearby, they'll fall at slightly different rates, and the tidal force between them is something which is independent of observer. So it's really only the tides that are the measurable things. And that's why to measure gravitational fields, you actually have to have two little masses. You can measure an electric field with one charge, but to measure gravitational fields, you always need two, because the tide is the only real thing. Okay, so here's my single line of force. Now what happens if I start moving this? So if I start moving the charge, the special relativity says that all the field lines still point towards that moving charge. Okay, so you see the field lines moving along with the charge across the screen. So what would happen if I started with a stationary charge and then I suddenly accelerate it and start it moving? Well, then the field lines have to connect between these radial field lines and the moving ones. But because the signal can only propagate out at a maximum speed equal to the speed of light, there has to be some kink joining the field lines far away that were how it was when the charge was stationary to what happens when they're moving. So let's see how that works. So here I suddenly accelerated this, and now here's the pattern of field lines of the moving charge, but this is still the memory of what it was before it was moved. And this kink is moving out at the speed of light, connecting those two field lines. So this is an example of producing an electromagnetic wave by suddenly moving a charge, and exactly the same thing happens if I suddenly accelerate a mass. The gravitational field lines get kinks in them, or if you think like the curved space, I accelerate the particle, the curvature near the body follows it as if it were stationary in the reference frame of the body, but far away it remembers what it was like before the object moved, and there's a kink, which is the gravitational wave that propagates out. Now, if I want to move a mass, it's very difficult to move large masses like the Earth, the Sun, or black holes just by pushing on them. So the easiest way to make a big mass move around rapidly is to put another big mass next to it and make them go around each other. And that then accelerates the two masses, and they produce gravitational waves. So that's the sort of simplest and easiest way to make gravitational waves, is just to put two bodies in orbit around each other. Now, those waves are propagating curvature in space-time, and I told you that curved space-time actually has energy itself. So these waves that are propagating actually carry energy. So if you look at the river wall, you can see water waves. The ship is pushing the water up ahead of itself, and then there's a dip and a little bump behind it, which I've illustrated here by tracing the tops of the waves. And if you look from above, you see this long wave train. So the waves are carrying energy away from the boat. And since they're carrying energy away, that must be coming at the expense of the kinetic energy of the boat. And so if I want the boat to keep moving, I need an engine. If I took the engine away, the boat would slow down and its energy would be carried off by waves. Now, two bodies orbiting each other are a little bit funny, because if I have a boat and I lose energy, it slows down. If I have two bodies that are orbiting each other and they lose energy, they speed up. So gravity is kind of a funny thing, and the reason is that the closer you are to a mass, the faster you have to go to orbit it. So if we start far away, moving slowly, and you lose energy, you fall deeper into the gravitational potential well, and you have to orbit faster. And of course, as you might guess, the faster you go, the more gravitational waves you emit. So as you lose energy to gravitational waves, you go around faster and faster and faster, emitting more and more waves. And so the in-spiral accelerates enormously. And you can see the same thing with satellites dragging through the Earth's atmosphere. They lose energy, they spiral in, they orbit faster, and eventually they crash into the Earth's atmosphere. Now, let's do a simple calculation. You all know, I think, that the moon goes around the Earth once every 27 days. And as you can check for yourself, during an eclipse of the moon is about 60 Earth radii away from the Earth. And some of you, I hope, will remember Kepler's laws or a little bit about gravitational force. So I apologize for those of you who don't like equations, but here's a simple one. So the period, how long it takes to go around, is the size of the orbit, 2 pi times the radius of the orbit, divided by the velocity, and the velocity is square root of g times the mass of the Earth over a. So the period, you can then work out, goes like the 3/2 power of this distance. So if I want to find out how long it takes a satellite just near the Earth to go around, the 1 over the period of the satellite is 1 over the period of the moon times 60 Earth radii, this distance, over 1 Earth radius, this distance. And that turns out to be a period of about 1.5 hours. So satellites go around the Earth just above the Earth's atmosphere in 1.5 hours, while the moon, much farther away, takes 27 days. So if I had something which was losing energy by gravitational waves and spiraling in, it started off by the moon and would end up at the Earth at 1.5 hours. And can it go any faster? No, because if it tries to get closer to the Earth, so it would go faster, it hits the Earth. So the gravitational wave signal from the moon spiraling in, if it doesn't emit enough gravitational waves for that to happen, but if it did, you'd have a gravitational wave signal that started off with a frequency of 1 over 27 days and ended up with a frequency of 1 over 1.5 hours. Okay, so let's now talk about the exciting event that you've all heard about. So this shows the gravitational wave frequency. The color is the intensity, how strong the gravitational wave was. It lasted for about 15 hundredths of a second. And the gravitational waves, I've conveniently put a piano keyboard here. This is middle C, right, if you could hear it. I mean, this is the bottom C of the piano keyboard. So it went from about 50 hertz, sort of an A at the bottom of the keyboard, up to about the C below middle C in 1/10 of a second or so, doubling in frequency. And then the signal ended. So if we interpret this as two bodies orbiting each other, that means that it started off with at about 50 hertz and ended at about 100 hertz. So we can now work out what is the density of the object that produced this signal. So if you look back at my little equation here, you'll notice that the period depended on m over a cubed. That's the mean density inside the orbit. So in terms of frequency, the maximum frequency that I can have the orbit squared basically determines the density of the object. So the maximum frequency that I can go around the Earth was once every 1.5 hours, or once every 5,400 seconds. The maximum frequency here is 100 hertz, 100 cycles per second. So the density of the thing which this was orbiting must be 100 times 5,400 squared times the density of the Earth, or about 3 times 10 to the 11 the density of the Earth, which is about 5 times that of water. So that means that the density of whatever was orbiting here must have a density of at least 10 to the 12th times the density of water. Okay, so that's 1/100th the density of nuclear matter. Okay. Now there's another thing that we can notice. This shows the sort of in frequency space. These are the actual waves that were detected. And you'll notice that there are about 5 wave cycles before the frequency is doubled. So you can work out with the theory of general relativity how many wave cycles it should take to double the frequency. And the answer is c, the speed of light, divided by the orbital velocity to the 5th power times the ratio of the big mass to the little mass that's orbiting it, and I've defined them in such a way that this ratio is always bigger than 1. So if I see this to be a few, that immediately tells you that these two masses must be about equal, and the velocity must be about the velocity of light. Okay? So if this is 2 orbiting bodies, they were orbiting each other at about the speed of light, they were about equal masses, and they had a density that was 10 to the 12th times the density of water. And you can deduce that without knowing any more relativity than I've explained here. Okay, so let's see, what could it be? Well, I love neutron stars. I spend lots of my life on neutron stars, very nice. But they have a density that's 10 to the 14 times that of water, so the maximum orbital frequency is 1,500 hertz. But the signal ended at 100 hertz, so it can't be a neutron star. Well, what about a black hole of 2 solar masses? Well, no, that would be even smaller than a neutron star, about half the size, maximum frequency of 3,000 hertz, going the wrong way. So what I actually need is a black hole which is much more massive than this, and therefore less dense. And you can show that the maximum frequency of orbits around a black hole basically scales like 1 over their mass. So if I want to get 100 hertz, I need to be 30 times lower frequency than this, or 30 times higher mass. So indeed, this is the configuration of the waves when they first got strong enough for LIGO to detect them. There's 2 black holes of about 30 solar masses, as we deduced, orbiting each other at about half the speed of light, separated by about 700 kilometers. And they did that for 5 orbits, and then it was all over. And what was over? Well, they put together and they made an even bigger black hole. So these diagrams are all to scale, so you put this plus this and you get that. And this black hole, we notice from the ring down, the little signals after the merger, was actually spinning. And the spins of black holes is really quite fascinating, because there's a region outside the horizon of the black hole where particles can really orbit, where if the black hole is spinning in this gray region, particles can only move in the same direction that the black hole is spinning. It's impossible for them to go the other way. And just to illustrate that, if I have a black top view, I have a black hole that's spinning around this way, and I send a particle in on the right-hand side, it orbits and goes into the black hole. If I aim it on the left-hand side, so it's trying to orbit in the opposite direction to the rotation, when it's far enough away, it can orbit in any direction at once, of course, but as it gets close to the black hole, whoops, it has to reverse its direction and go in the other way. Okay, so the black hole spins really, they drag space-time with them and make everything rotate with them. Okay, now, so I've told you everything you need to know about gravitational waves. You've deduced that there are 30 solar masses. I hope I've convinced you that was probably 2 black holes. But how did I get the 29 and the 36 and the spin of 0.87? I actually need a little more information than I've given you so far. So I just wanted to illustrate for you that if you've actually computed lots of sound templates before, you can have a pretty good idea of what comes before and after in the details. I hope you all know what that was. You know, it was only 4 notes. The LIGO waveform is about 4 notes, but I think you all probably know what comes after that. Oops. Okay, so you all guessed that, I trust. Oops, no. So let me try one more example. Only 3 notes. I think many of you probably guessed what comes after that. Okay, so templates are very useful. So how do we get templates for Einstein's equations? Well, doing 2 orbiting black holes merging to make a single spinning black hole is not something that we're going to do with pencil and paper, I can confidently say. First of all, to find the solution for 1 rotating black hole not perturbed by anything took mankind 48 years. 2 merging black holes is not practical. And one of the reasons is that Einstein was very generous in his equations. You can use any choice of coordinates you want to describe the space-time, but only a very small few choices of coordinates will actually not have singularities and cause your computer to crash while you try to calculate. So one of the hardest problems is to figure out how to choose those coordinates. So that was finally, after 40 years of hard work by hundreds of very smart people, in 2005, a postdoc at Caltech finally got the first black holes to go around each other once and merge and produce a waveform. And that waveform from 2005 looks remarkably like the LIGO signal, I have to say. Okay, so that was 1. Let me pass over this. We now have hundreds of these things computed with spinning black holes with different directions of spin, different mass ratios. That case I showed you was 2 equal mass black holes. So you can use these as templates, just like your previous hearing of Beethoven's Fifths and Eine kleine Nachtmusik. You can match these against the gravitational wave signals seen by LIGO and determine the parameters of the signals. So let me conclude by just describing what we've learned. So to me, the most remarkable thing is that black holes are formed by curving space-time in a very strong way. We didn't really know that they actually existed. Things that acted sort of like black holes with things orbiting each other at high speeds existed, but actually knowing that they really were described by Einstein's theory and that they got put together in the dynamical way that Einstein's theory predicted was, I think, really a tremendously exciting new event. And it required 50 years of very hard work, both experimental and getting that numerical relativity to work was 40 years of very hard work. Let me just talk a little bit about the future. I think other speakers will address this. LIGO is sensitive to a little range of frequencies between about 30 hertz and 1,000 hertz. There's a whole spectrum from 10 to the minus 17 hertz to 2,000 hertz. This is 1 over the age of the universe. So, for example, supermassive black holes, like the one in the center of our own galaxy and our neighboring Messier 31 galaxy, have black holes that will be detectable at sort of frequencies from 1 over a few years up to 1/100th of a second when they merge. They're ordinary stars and supernovae. They're mountains and distorted neutron stars. There are phase transitions in the early universe when it was 10 to the minus 36 seconds old, and then again when it was temperatures of TeV. You can have phase transitions and bubbles crashing into each other at the speed of light can produce gravitational waves. There can be cosmic strings left over from different phase transitions that whip around in the universe at the speed of light, producing gravitational waves. So we've got our first little glimpse of the first object in this high frequency region, but there's a whole spectrum from frequencies of 100ths of a second periods down to the age of the universe, and that's waiting to be explored from space, from timing pulsars, from the cosmic microwave background. And I think this is just the beginning of gravitational wave astronomy. So.
Thank you very much, Chancellor.